Hello, everyone. My name is Michaela Huffman. I am currently finishing up my undergrad at the College of William and Mary, which is in Southern Virginia. And today I'll be talking to you about my poster on a systematic search for low velocity secondary craters of secondary craters, aka tertiary craters, on the moon. This is abstract number 2018 for LPSC53. And although it may look like I am floating above the Lunar Reconnaissance Orbiter camera's wide-angle camera mosaic, I'm actually just upstairs in the Woodlands Marriott. So let's hop right into it. Let's take a look at my poster. Awesome. So I am doing this research for my undergrad physics honors thesis with Dr. Kelsey Singer, who is at the Southwest Research Institute. And this was partially funded by NASA's Solar System Workings Program. So yeah, let's talk about it. So first I want to give you a quick primer on primary, secondary, and tertiary impact craters. Extraterrestrial impact craters are useful for geochronology, planetary formation, and placing empirical constraints on dynamic fragmentation theory. If we count the number of primary impact craters on a surface, it can help determine its age. But each impact event on the moon throws out ejecta, which can re-impact the surface, creating secondary craters. If you count all the secondaries as primaries, that's really going to mess up your geochronology. And in addition, dynamic fragmentation theory would benefit from looking at very low velocity planetary data, akin to the types of experiments we tend to do on Earth. So if we take a look at this image, it can help clear up kind of that primary versus secondary versus tertiary. For the math that we do, we assume that these fragments that create secondaries are launched at half the transient crater radius at approximately a 45-degree angle. And then they re-impact the surface, creating secondary impact craters. Secondaries may in turn go through this similar process, creating their own secondaries, which are called tertiaries. So again, they get launched out and then land creating tertiaries. There are a few mentions of tertiaries in the literature, but this is, as far as we know, the first concerted search for tertiaries using high resolution imagery of the moon. Talking about that high resolution imagery, it's from the Lunar Reconnaissance Orbiter camera's narrow angle camera, LROC-NAC. And in this work, we present a potential set of tertiary impact craters from a small, which is about 1.8 kilometers in diameter, fresh primary crater to the south-southwest of Blushko crater on the moon. And we refer to this unnamed primary crater as Wallace, just so I don't have to keep saying the small, fresh, unnamed crater to the south-southwest of Blushko. All right, let us forge on talking about image processing and analysis. So for our initial search, we used the LROC wide angle camera, the WAC global mosaic, the thing behind me, and NAC images as viewed on the LROC quick map as a base map. Then we chose some NACs, then we processed these images using the USGS's ISIS program. We analyzed and mapped these processed images in ArcGIS Pro using geodesic distances. The WAC was used as context for these NACs, and then we mapped those actual potential tertiaries as well as secondaries of this primary on those higher res NACs. We focus on small, fresh lunar craters. Now you may be thinking, well, okay, a bigger primary means bigger secondaries, which means bigger and easier to see tertiaries. Why don't you look around large ones? Well, we did. Initially, we searched around larger and more visible primaries, including relatively young large primaries like Tycho crater, expecting that these would yield those larger and more visible tertiaries. However, even for somewhat young larger primaries, their secondary fields have degraded significantly over time. So we looked around Petavius B, Tycho, Giordano Bruno, and Oriental, and didn't find any tertiaries. So then we started looking around small, fresh ones. Okay, well, let's talk about Wallace and Grommet and potential tertiaries. So Wallace crater, again, it's unnamed, is 1.8 kilometers in diameter. And it's located at about 79 degrees west and 3 degrees north. So let's take a look at that in context. So right now we are on the edge of Oceanus Procellium, pretty near to the equator. So let's zoom in here around Tertiary crater. And that's this red box here. And you can see we see Tertiary crater. And then to the south-southwest, we see this very fresh young crater. So let's zoom in on that guy. We're now going to the orange box. And as you can see, it's got this very high albedo, fresh ejecta blanket, which is exactly what we're looking for. Not very degraded. And Wallace is, again, about 1.8 kilometers in diameter. All right. So we mapped a lot of secondaries of Wallace. Specifically, to date, we've mapped 8,827 secondary craters around Wallace. And interestingly, there is a cluster of large secondary craters 9.6 kilometers to the north-northwest. So that's what this this yellow box is. So it's about 9.6 kilometers to there. So let's zoom in on that. We're taking a look now at this yellow box labeled 2D. And one of these craters I'm going to lovingly refer to as Grommet. And then I didn't come up with a fun name for this one, but the secondary crater just to the south of Grommet is also one that we're looking at. Grommet, measured along the short axis or the minor axis, is about 62 meters in diameter. And the small, the secondary to the south of Grommet is 41.5 meters along that short axis. Downrange of Grommet and also downrange of this secondary just to the south of Grommet are potential tertiary craters. This is very exciting. So let's take a look at those. I'm going to zoom in a little bit more. Looking at this green box, we're now on figure 2E. Oops. So here we have Grommet right here. And then again, also the secondary just to the south of Grommet. Again, Grommet is 62 meters along that minor axis, and the secondary just to the south of Grommet is 41.5. So let's talk about these things that I've circled in yellow. These are elliptical dents whose long axes tend to point back towards Grommet, and they often have associated downrange boulders. Those are circled in blue. So let's talk about those for a second. Let me zoom in a little more. 2F and 2G are both that blue box that I have boxed, but I would like you to note that we don't just see these only downrange of Grommet. Additionally, we see some to the south, well, to the west of Grommet that are associated more closely with this secondary just to the south of Grommet. So these are elliptical dents marked in yellow. And as we can see in figure 2G, which is right here, the long axes of these dents tend to align more closely with the radial indicators from Grommet, which are in green, than with the red radial indicator from Wallace, which is the primary. So the long axes tend to point more in the direction of Grommet, that secondary, than to that coming from Wallace, which is the primary in red. And you can even see with the associated boulders, they continue that trend. All right, well, let's talk about these guys a little bit. Using only dents that are more than 3 pixels across. So we're pretty sure we know what we're looking at. They're not just tiny divots in the landscape. And ones that are unlikely to be attributed to any other secondaries in the area. So for example, looking back at this yellow section, you can see that there's several other potential craters. Hello. Technology in the area. So for example, any of these elliptical dents that we see kind of in this region, they could be attributed either to grommet or to this other secondary. And so we do not include those in our count. So only ones that are more than 3 pixels and that are unlikely to be attributed to any other secondaries in the area aside from grommet. We have a sample size of 21 potential tertiaries. These dents are on average 6.8 plus or minus 1.9% the size of grommet. And this is a useful number because there's a rule of thumb, which is that the largest secondary craters tend to be 4 to 6% the size of their productive primary. And since tertiaries are just secondaries of secondaries, this is a useful number. So this value is somewhat on the large side, but it's still similar to typical values of the secondary to primary size ratio, including within error bars. All right, well, we'll pop back to these plots in a second, but I want to walk you through some logic now. So for these suggested tertiary craters to actually be tertiaries, they must be secondaries of grommet, or the secondary just south of grommet, which in turn must be secondaries of Wallace, that primary crater. So first, let's ask the question, are grommet and the crater just south of grommet actually secondaries of Wallace? So usefully, grommet has several characteristics that align with secondary crater features. So let's take a look at grommet. It is apparently shallow compared to other craters of its size in the region. So for example, looking at this guy versus grommet. And there's some that are off screen that are more comparable in size to grommet. It has a poorly defined downrange rim. So if we look over here, that downrange rim is pretty poorly defined. In addition, it has V-shaped ejecta, which I have marked with red V's on figure 2E, but you can see it unmarked in figure 2D. It is about 3.3% the size of Wallace, which falls below that 4 to 6% rule. So it is not way too big to be a secondary of Wallace. And if we take a look at this first figure here, figure 3, it's not abnormally large for its distance from Wallace. So let me walk you through this figure. On the x-axis, we have the distance of the center of these secondaries from the center of the primary. And we are looking at secondaries of Wallace, so we have quite a large number here. On the y-axis, we have that secondary crater diameter, again, looking along the short axis. So for example, if this is the elliptical crater dent from that of a secondary, we're looking at the minor axis. So this is a distance diameter relation of Wallace's secondary craters. And we can see marked on this plot in orange with the convenient arrows, grommet and the secondary just south of grommet. So as you can see, they're not so large for their distance that it would be unreasonable for them to be secondaries of Wallace. For example, if grommet were, closer to 90 meters across and out 30,000 meters, like here, it would be a bit harder to make the argument that grommet and that secondary just south of grommet are actually secondaries of Wallace. So let's say, hypothetically, all of these indicators that show that grommet is probably a secondary of Wallace are completely wrong. Well, if grommet isn't a secondary, then there's a couple of options. It's either a primary that is overlying Wallace's ejecta blanket. So the Wallace impact event occurred, and then grommet came down and landed on top of that ejecta blanket, or it's an underlying primary. So it occurred, and then the Wallace impact event occurred and scoured it to give it kind of that appearance. So let's tackle that first one first. It is pretty unlikely that grommet is a primary crater overlying Wallace's ejecta. It's not morphologically similar to overlying circular primaries in the area. Again, you can take a look there. There's a couple other ones that are off screen, but for example, that is more likely to be a primary. It just doesn't look like grommet. Grommet has radial features that are in the same direction as Wallace's ejecta. So for example, that V shape, its ellipse tends to align with it. Grommet is elliptical in the downrange direction of Wallace. And the elliptical dents and their associated boulders are downrange of grommet. If grommet were a primary crater not associated with Wallace, it would be surprising, but not impossible, that all of the elliptical dents that can be attributed to grommet were downrange of both grommet and Wallace. So what I'm saying is it would be really weird for all of these kind of elliptical dents to be arrayed in the area where they are, in the orientation that they are. And we don't see any that are more so like this or like that. We don't see those. Okay, so it seems unlikely that grommet is a primary crater overlying Wallace's ejecta. Well, let's talk about if it's an underlying primary that got scoured by Wallace's ejecta. It cannot be ruled out. It's more likely than the overlying hypothesis. Grommet is not as scoured as other underlying features in the area, but that may be due to its larger size. Again, at 62 meters along the minor axis. Grommet's rims are not as distinctive as some of the other secondaries in the area. So if we take a look back over here, you can see that the potential secondary just to the south of grommet has nicer defined rims, as you can see here and there, compared to grommet. So that seems, a little fishy, but all secondaries might not form in the exact same sequence with emplacement of other smaller ejecta fragments that form this kind of disturbed soil/ray pattern, but do not make distinct secondaries. So not all secondaries look alike, basically. And the downrange dents are not obviously scoured in appearance, which lends credence to grommet not just being a scoured primary. We can follow through the similar logic for the crater just south of grommet, which again also has associated tertiary dents here. Oh, sorry about that. I can even point that out to you in figure 2D right here. Yeah, so you can see the tertiary dent right there. Sorry, maybe I should use a finer pen for this one. There is that tertiary dent, and then there is the associated bolide. So we can follow pretty similar logic. We conclude that grommet and the crater just to the south of grommet are low velocity, are secondaries of Wallace, but we can't really rule out that they could be scoured underlying primaries. Either way, if they are secondaries or if they aren't, the elongated dents and downrange boulders that we see are low velocity ejecta with very interesting properties. So let's take a look at some of those properties. This here is a plot showing the distribution of the elliptical tertiary dents minor axis lengths. So again, there's that elliptical dent, and we're looking along the minor axis. And so we have the minor axis length in meters on the x-axis, and then the frequency on the y-axis. Only dents that are larger than 3 pixels that were unlikely to be from any other secondary other than grommet were used. So you can see that we have some that are just a tad under 6.5 meters along that short axis, and some that are closer to 3. All right, well, some of these dents have downrange associated boulders. So let's take a look at that size distribution. So we have the boulder / tertiary projectile size on the x-axis and its frequency. This was done by taking a look at the boulder and then just drawing a line across it. Again, these are all geodesic distances. And again, only boulders that we can attribute to dents that we can attribute to grommet that are bigger than 3 pixels in diameter. The most frequent value lies between 2 and 2.5 meters, but we have some larger than 4.5 and some that are closer to 2 meters. All right, well, before I get into those fun rainbow plots, okay, let's assume the secondaries are secondaries. If the secondaries are secondaries, can we determine if the tertiaries are actually tertiaries? Okay, so this is basically asking, are those tertiary dents secondaries of grommet and the crater just south of grommet? Those dents associated with grommet are on average about 7 ± 2% the size of grommet, which we talked about earlier. Within uncertainty falls in that 4 to 6% rule of thumb. They tend to align with radial indicators from grommet more so than with radial indicators from Wallace. Again, looking back at figure 2G. And they kind of fall into this transitionary zone between boulder tracks and secondaries, which is what we would expect from small secondaries. So they're elliptical with downrange boulders. And so we conclude that the small elliptical dents are likely to be tertiaries, assuming the secondaries are secondaries. So let's take a look at the velocities associated with these. So this plot, which I like to lovingly call the rainbow plot, we have the velocity of the fragment that produced the tertiary dents downrange of grommet at various ejection / impact angles. So let me talk you through this. On the x-axis, we have the velocity that the bolide that produced the tertiaries came in at. So going back to this useful figure 1, we're talking about the velocity that the bolide had both at the time of ejection and at the time of impact. Because we're working on the moon, and the moon has no appreciable atmosphere to slow a bolide on a ballistic trajectory, we assume that the ejection and impact angles are the same in all the cases that we calculate. And we are using equation 5 from Singer et al. 2020, which is the ballistic range equation on a sphere. And we're using the geodesic distances from the center of grommet to the center of the tertiary dents as the input for that. So we're using a range of ejection / impact angles, which again are assumed to be the same. So red is 5 degrees, orange is 10 degrees, green is 15 degrees, blue is 30 degrees, and purple is 45 degrees. We assume that the fragment is launched at half transient crater radius as well. And then on the y-axis, we have the frequency. So as you can see, for the lower or more elliptical ejection and impact angle, we have to get a higher velocity to account for that. So we have some tertiaries that were formed from bolides going about 80 meters per second at the fastest to around 40 at the lowest. And if we go to kind of a higher ejection / impact angle, closer to 45, we can see that we get some velocities that are sub 20 meters per second. So in addition, well, we we've been seeing all this stuff about these downrange bolides, which are so interesting because we don't typically see that for secondary impact craters. So the fact that we're seeing the actual bolides that we can associate with these tertiary dents is really, really interesting. So after the bolide produces a tertiary dent, it can bounce out and then land further down range. So after it produces the dent, it can bounce out and then land further down range. This plot, this rainbow plot, similar to the one that we showed above in figure 6, shows a distribution of that bounce velocity. So the velocity after it forms the dent, it gets ejected or bounced out of that tertiary impact crater and then lands further down range. So this plot shows a distribution of that bounce velocity. And again, we're only using boulders that could be attributed to dents that are greater than 3 pixels that were downrange of grommet. So as you can see, we're using the same angles, more elliptical impact angles at the top to 45 degrees at the bottom. And again, we see higher velocities for that 5 degree versus lower velocities for that 45. But these are pretty low velocities. So we see more than 20 meters per second for that bounce velocity for the 5 degree end member case. And then we see sub 5 meters per second velocities for that higher ejection angle. And so you can see that there is a bit of kinetic energy that is lost in between figure 6 and figure 7. All right, time for conclusions. So overall, we have found a field of 55 greater than 3 pixel tertiary craters around a 62 meter diameter secondary crater, grommet, from a 1.8 kilometer diameter primary crater, which we are calling Wallace. We did this on NACs from the Lunar Reconnaissance Orbiter camera. The resolution of those NACs was about 0.88 meters per pixel. Through this work, we are probing the lower limit of velocity in terms of what will create a secondary/tertiary crater on the moon. And looking back at figure 6, we saw so far that we have found tertiary dents down to possible impact velocities as low as 20 to 30 meters per second for lunar gravity. These tertiaries have interesting morphologies that can help us understand low velocity crater creation. And there's a ton more work to be done. So we will continue to search for tertiaries around more young, fresh lunar primaries. We plan to compare the velocity and fragment sizes of these potential tertiary craters to ejecta theory predictions using that dynamic fragmentation theory. Hopefully looking at low velocity, small impact craters can, planetary data can help align some of that theory. And in addition, we are going to look at that change in kinetic energy. So we see kinetic energy loss from the bolide forming the dent to it bouncing out of that tertiary. And so maybe taking a look at how much energy is lost there and looking at lunar regolith properties to try and determine if that's viable. So overall, tertiary impact craters, pretty cool. They exist. We would like to thank NASA's Solar System Workings Program for funding. Here are our references. If you would like to chat about this, I would love to talk. My email is here, michaelarhuffman@gmail.com. Yeah, thanks so much for listening and watching.